test tubes, and welcome to a BMO preparation video. Two things though before I start. I'm sorry for the terrible lighting, I moved recently. And secondly, although full solutions will be provided to each of the questions I do, the aim of this video is actually to explain how I'd go about thinking when I see the problem first. So if you're completely stuck at a problem, how you should like bash at it, etc., or just seeing a problem for the first time. And also, if there's like lots of stuff to write, I probably won't write everything. I'll just tell you what to do because that's long and not something good for videos. So for question 1, we have two intersecting circles. They intersect at N and M, and we also have their common tangent, BQ. We want to show that the areas of the two red triangles Q and M and P and M are equal. I think when I first drew this, I extended this line as well because the line connecting the two intersections of the two intersecting circles can be very important, and I marked this point as T. And I again reminded myself that QNM and PNM have to be equal. And wouldn't it be great, right, if QTM and PTM were equal in area, and then QTN and PTN were also equal in area? Because if the two big triangles and the two small triangles are equal in area, then their difference, the two red triangles, will also be equal in area. And in fact, this sort of simplifies our problem, but sort of doesn't, because when are PTN and QTN equal? Well, they share the same altitude to the tangent PQ, so they will the triangles will be equal when their bases are equal. So when TQ and PT is when TQ is equal to PT, and the same goes for when TMQ and TMP are equal, because they also share the same altitude, so we need TQ to be equal to TP. So we actually only need to prove one thing. We need to prove that TQ is equal to TP, and if we prove that, then we've proven that the big triangles are equal, and we've proven that the small triangles are equal. So how do we go about proving that PT is equal to TQ? I couldn't really figure out a way I could say how I thought of this, because I do know about a thing called the tangent second theorem, which is if you have, or I don't know how it's called in British, probably tangent second. If you have a point O, P, M, N, then OP squared is equal to OM times ON, where P is the point of tangency. And this is fairly easy to prove. It goes like this. We have these two triangles. Now this is a tangent, so this line is this angle is going to be equal to this angle, and so the two triangles are similar. The triangle NPO and NMPO are going to be similar because they have two angles which are the same, this angle and this angle, and obviously the angle at O. And so this is going to mean that the long side of the big triangle, so ON, divided by the side of the big triangle that's opposite the angle that I denoted, so OP, ON over OP, is equal to the long side of the small triangle, so OP, over the side of the small triangle that's opposite to the angle that I denoted, so OM. And from this you have that ON times OM is equal to OP squared. This is a fairly standard theorem in Olympiad mathematics. I know that it's not required in BMO Round 2 if you read the spec. So there's probably another solution that doesn't involve this, or you have to come up with this by yourself. But I couldn't really think of, or at least I was too lazy to think of a solution that didn't involve this. So if we know that P squared is equal to OM times ON, let's look at how to apply this to here. We know that TP squared, so the length from t to the tangent squared is equal to tn times tn times tm. But we also know that tq squared, so looking at this circle now, the length from t to the tangent is equal to the product of the segments of the second, so tn times tm. And from this equality we get that tp squared is equal to tq squared, and because both lengths are positive, tp equals tq. So we proved that TP equals TQ, and from reasoning that I showed earlier, we've also proven that the areas of big triangles are equal, the areas of small triangles are equal, and so the areas of the red triangles will also be equal. So for question 2, you're given that xyz is equal to 32 and all of xyz are larger than 0, and you need to find the minimum value of x squared plus 4xy plus 4y squared plus 4z squared. Do note that basically in BMO, I think there's 2 standard techniques I'd apply to inequalities or like minimum finding things, but mostly inequalities. And I mean, I'm sure there's lots of other things that I haven't noted yet because I don't do so much BMO stuff. But what I tend to bash at first is either turn this into something symmetric, so like you have x squared plus 4xy plus 4y squared plus 2z squared, but your numbers of x squareds aren't equal to numbers of z squareds, and neither is your number of xy's equal to your number of yz's or xz's. So you could just add y squared plus 4yz plus 4z squared plus 2x squared, and then do the same thing where you where you shift the x, y, z again, and then you get 3 times your minimum sum, because your minimum sum for x squared for this thing is going to be equal to your minimum sum for this thing if you just change the values of x's and y's and such. But this doesn't seem to be what they want, especially in minimum findings. This would work very well in inequalities, but here it wouldn't, because the minimum value of this thing happens at some specific x0, y0, z0, and that same x0, y0, z0 isn't going to be the same here. So your x0 would actually be your y0. So y1 equals x0, etc. It's not the same thing. So don't do that here. And the second thing that I would suggest looking at is AMGM. So you know that x squared, if that was your A plus 4xy, that's your B, plus 4y squared, that's your C, plus 2z squared, that's your D, that's larger or equal to 4 fourth roots of A, B, C, D. Let's look at the fourth roots of A, B, C, D. That's x squared times 4yx times 4y squared times 2z squared, all to the 1/4, giving me x, so that's 1632 x cubed y cubed z squared to the 1/4. And see, this is bad, or at least it's not bad, it's very close to what we want, because what we would love to have is x cubed y cubed z cubed, because then we would know what x cubed y cubed z cubed, we do know what x cubed y cubed z cubed is, it's just 32 cubed, so we would know the minimum value, or at least we would know a minimum value. And so what makes us unhappy is that here there is 2 places where x appears, 2 places where y appears, so the total sum of powers is going to be 3, and for z it's only 2. Big sad. Oh yeah, so what can we do? Well, a quick reminder that x squared plus 2z squared, that would be over 2, let's say, that's bigger than square root of x squared times 2z squared, but also x squared plus z squared plus z squared over 3 is larger or equal to cube root of x squared z squared z squared. And this, I think, is the part of the solution that's hard to come by, because you can try this out and then you see that your z doesn't work. So what do? And you try to separate the x's and y's all over here into x's and y's that will be happy together. Yeah, so let's look at how you could separate them. If you look at the x squareds and y squareds, they're going to appear, the xy's are going to appear and give like a total sum of the power of x and the total sum of the power of y's, the same number. So you do really want the number of y squares, not the number of y squares, but the number of times y squared appear in the sum. So 2y squared plus 2y squared is a different number of times y squared appears to 4y squared, because here it appears only once and here it appears twice. So you want the number of x squares and y squares to appear at the same time. So you have x squared plus 4y squared. This stays. And for now, you have x appearing twice. Sorry, x squared, the power of x squared being 2, power of y squared being 2. And if you get then plus some number also positive, because you have to add this in, so some positive. And then for z squares, for z squared, you have 2z squared if you don't break up the z, and that's only 2. So for the total power of x squared, that's going to be 2 plus something positive. And for z squared, if you don't break it up, it's going to be 2. And you don't want that. You want them to be equal. So let's break up the z. If we break up the z, well, we do kind of want to keep the things integers. So I'm going to break it up as plus z squared plus z squared. And then let's finally look at how to break up for yx. So we have z squared plus z squared, giving a total power of 4 for our z, plus x squared plus 4y squared, and here each of them has a power of 2. So we kind of want to add two powers of 1, because there's a maximum power of 1 here. So we could add plus yx plus 3yx, or we could add plus 2yx plus 2yx. And I mean, you can try out both and see which one's right, but for me, because x, y, z is a power of 2 and we have power of 2 and the y's here, I'm going to do the plus 2yx and 2yx. So that gives me plus 2yx plus 2yx. That's our sum, which is larger or equal to 6, because there's 6 things being summed, 1, 2, 3, 4, 5, 6, times z squared, x squared, times 4y squared, times 2yx, times 2yx, to the 1/6. And working on our inequality just a little more, just with algebra, I've shown these 2 steps and up to here, and then if you play around again, you get all of this is larger than 6 times 2xyz to the 2/3, and 6 times 2 times 32 to the 2/3 is equal to 6 times 64 to the 2/3, and 64 is 8 squared, so is equal to 6. Oh, I can't do maths. And 6 times 8 to the 4/3. Wait, no, not 6. 8 to the 4/3, and that's 6 times 2 to the 4, which is 6 times 16. Okay, so we found a minimum value of this, but we don't know that this minimum value is actually reached. So our function, I'm not going to draw in, what is it, 4D, the function, because I can't, but this could be our minimum value, so this could be 6 times 16, and our function does something like this and then goes up to infinity or whatever. And so there is a better minimum value right over here that we haven't mentioned, and that wouldn't do, right? Because we could just say that a minimum value of this is -1 and everything would be good, because that is a minimum value, but it's not a value, it's a minimum. But yeah, and you need a minimum value, so you need to find where this value 6 times 16 is actually reached, or if you can't find this, then find a better minimum value, because that's not a minimum value. Anyways, so how do you do this? Well, AM is equal to GM, that's when the minimum value is reached, and this only happens when all of the summated things are equal. So when x squared is equal to 2xy is equal to 2xy is equal to 4y squared is equal to z squared, which is equal to z squared. And that's when x squared equals z squared, they're both positive, so x equals z, and x squared equals 4y squared, so x equals z is equal to 2y. And this makes sense for the fourth equation, because 2 times x times 2y is indeed equal to x times x, which is x squared. So this all works, it's all consistent. Let's find the value. Well, we know x, y, z is equal to 32, so 2y times x, z is equal to 64. 64, and that's when x is equal to the cube root. This is all x cubed. X cubed is equal to 64, so x equals 4. So at x equals 4, z equals 4, and y equals 2, x equals 4, z equals 4, and y equals 2. Let's see what the sum is. Well, we have 16 plus 2 times 2 plus 2 times 4 times 2, that's also 16, plus again 16, plus 4 times 4, which is 16, plus 16, because z is 4 plus 16, and that's 1, 2, 3, 4, 5, 6, equal to 6 times 16. So our minimum value is actually reached, and everything's good because we did a good solution. Number 3, you're supposed to find an A and B such that this equality holds, and A and B have to be integers, positive integers, I think. And so the first thing to do is see if you can come up with anything smart and interesting, and if you're like me and you can't, then you start expanding brackets, which is, I think, one of the most amazing things in maths. So you get cube root A squared plus cube root B squared plus 1 minus 2 cube root A minus 2 cube root B plus 2 cube root AB, which is equal to 49 plus 20 cube root 6. And let's take away the 1 here and put the 48 here. I don't know why, maybe that's a bad idea, but I did that and it worked. So first thing I had problems with was cube root A squared and cube root A, because if A isn't a cube, then A squared won't be either, and vice versa. So we need either these two to cancel out, which doesn't look like it would, because you'd have cube root A times cube root A, and then you'd have 2 times cube root A, so you'd have like cube root A minus 2, and this isn't, if cube root A, if A isn't a cube, then this is going to be the bad, and both A and B can't be cubes, because then you don't have the cube root 6 part, because all of these are going to be whole numbers. Okay, so either there's a problem with the cube root A minus 2, or there's a problem with cube root B minus 2, and they're not going to be whole numbers. So you need the cube root B to cancel out the cube root A squared, or the cube root A squared, sorry, the cube root A to cancel out the cube root B squared, or maybe this to cancel out something, but I'm going to focus on the cube root. I want cube root A squared minus 2 cube root B to be equal to 0. Let's look at how we can do this. Cube root A squared is equal to 2 cube root B, so A squared is equal to 8B. Okay, so let's look at the situation in which B is equal to A squared over 8. Maybe, just maybe, we'll find something good. Then we have cube root a squared and 2 cube root a already cancel out, so let's not look at that. Then cube root b squared is going to be b is equal to a squared over 4, so that's a to the 4 over 8 squared. So I'm just going to put this over 4 because I know that the cube roots cancel out for the 8, and then minus 2 cube root a plus 2 cube root of a, and then a squared over 2 because it's over 8. So and that's equal to 48 plus 20 cube root 6. Then doing a bunch of algebra on here, we have a times cube root a, 4 times cube root a minus 2 times cube root a plus a is equal to 48 plus 20 cube root 6. And we want this to work. We want this to work. We don't want cube root a to be an integer, so we want, in fact, this whole part is going to belong to the cube root 6 part, and the a is going to belong to the 48 part. So we know that a is equal to 48, and let's see if this works out to be 20 cube root 6, because if it doesn't, then we're going to have to find some other thing where b isn't equal to a squared over 8. Let's look at this then. We have a over 4 is going to be 12 cube root 48 minus 2 cube root 48, which is equal to 10 cube root 8 times 6, which is 20 cube root 6. Oh, how good. Great. So we know that a is equal to 48 works, and we know how to determine b from here. B is going to be equal to 48 squared over 8, so that's 8 squared times 6 squared over 8, and that's 8 times 36, which I'm not going to count because I can't. But yeah, that's the solution. For number 4, part A, find a set of 10 positive integers such that no 6 distinct elements of A have a sum which is divisible by 6. Here I say just play around with numbers. It might take you a really long time, it might take you a really short time if you stumble upon the correct way to construct them really quickly. Don't take too long on it, but I think that's the only way you can come up with a solution. So mine was 6, 12, 18, 24, 30, 7, 13, 19, 25, 31, and you can show by yourself that this sequence of 10 integers does indeed satisfy the conditions. Okay, so next up we have B. Is it possible to find such a set if 10 is replaced by 11? Well, firstly, let's look at what the two things that could happen. It could be a yes, in which case you should bring up an example. This being the 4th question of the British Mathematical Olympiad is probably going to be pretty difficult, so you'll have to find a way to come up with this example, but at the same time you could just stumble upon it, which would be absolutely ridiculous. So it's probably going to be a no, and I'm going to work with the assumption that the answer is no from now on. And secondly, because we know that the answer is no, I'm basically getting really major Pigeonhole principle vibes, just because there's 11 things, and yeah, there, you get it, basically. And so the problem now is to find what to pigeonhole. And at first I decided to pigeonhole the remainders modulo 6. There's quite a few remainders modulo 6, in fact there's 6. And that's a lot of work, and I ended up not getting anywhere, so I was like, well, 3 divides 6 and 2 divides 6, so we could look at remainders mod 3 and remainders mod 2, and this is much more useful because they are in fact smaller than 3. So if you have if you look at remainders mod 2, if you have 3 different numbers, then you will get 2 of them which are the same mod 2, and if you have 4 different numbers, mod 3, then you will find two of them which are the same mod 3. This is very useful, and I pigeonholed that for a while. And yeah, I'm in fact certain that you can get somewhere, especially with mod 3. You can just sort of construct little patches of 3 or of 2, which, yeah, of 2 is better, or 1 of 3 and then the rest of 2, which are the same mod 3, and work from there. But that was a lot of work, and I did end up getting somewhere, but the working is quite long as opposed to what I came up with next, and that is to look at the 11 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and use what I explained here. So if you have at least three different numbers, then you'll find 2 which are the same mod 2, which means you'll find 2 the sum of which is even. Those two statements are equivalent. Yes, they are. And so I can break up, I can find a pair, the sum of which is even in 11 numbers, and then in 9 remaining, and 7, 5, and 3 remaining. So I have 5 pairs, the sums of which in the pair is even, and so the remainder modulo 6 of each of these 5 pairs can be either 0, 2, or 4. And let's look at the different situations that arise. If there are 3 pairs that are the same, have the same sum mod 6, so if there's 3 that are 0, 3 that are 2, or even 3 that are 4, everything's good, because you can take these 3 and you'll give 6. You'll get 6 numbers that sum to 0 mod 6. Or imagine that's false, and in fact that there are only the maximum number of the same remainders mod 6 is 2. So there's maximum 2 of, say, 0, maximum 2 of 2, and maximum 2 of 4. Well, in that case, you can pigeonhole and realize that there will be at least one of each. Because if there wasn't at least one of each, then you'll get a maximum of 4, and the 5th will belong to nothing. And so you have a remainder of 0, you have a remainder of 2, you have a remainder of 4, and if you sum all of these together, you will also get 0, because 0 plus 2 plus 4 equals 6, which is 0. And so you'll always have 6 that are the same mod 6. You'll always have a number of 6 in a set of 11, a set of 6 in a set of 11 that sums to something divisible by 6. Yeah, thanks so much for watching. I hope that your exams go perfectly well.